Hello, welcome to this lecture on modeling analysis and estimation of three-phase unbalanced power network. In the last lecture, we were talking about one example, and in this example, one data we have not mentioned, and that data is that this length, this is a 40-mile long conductor, or rather this is basically a 40-mile long line. So, now what we are now going to do is that we need to find out the all these parameters of this Z impedance matrix. Now, for that we have to first calculate the value of omega k. Now, what is omega k? K is actually 2 into 10 to the power minus 7. So, then therefore, it would be omega is 2 into pi into 60, k is 2 into 10 to the power minus 7, but please note that this is essentially 2 into 10 to the power minus 7 is basically for Henry per meter, right. Now, because it is per mile, so then therefore, what I have to do now that 1 mile is equal to, so this we need to understand, 1 mile is equal to 6093, 1.6093, it is 1.6093 kilometer. So, that is equal to 1.6093 into 10 to the power 3 meter, right. So, then therefore, because the unit of this quantity, that is k, is basically 2 into 10 to the power minus 7 Henry per meter. So, then therefore, we have to express everything 1 mile in terms of meter. So, then therefore, it would be is equal to 1. So, then therefore, omega k would be 1.6093 into 10 to the power 3, correct. So, that would be per mile, right. So, now it would be basically per mile. So, if we do this calculation, we will find that is given by 0.12134. This is, and this unit is per mile, right. So, this is per mile. So, now what would be the value of ZA? ZAA, as we know that it is RA plus RD plus j omega k log dE by dSA, right. So, that was the expression. Now, RA was 0.278. What is the value of RA? RA was 0.278. So, it is RA is 0.278, RD is RD is given by 0.09528. Everything we are doing per mile, 0.9528 plus j into 0.12134 into log dE is 2790 divided by 0.01. You see, DSA is nothing but 0.01668, 0.01668, right. We have just used these values. So, if we do this calculation, we will find that it is 0.3733 plus 1 j 1.4594 omega per mile. Now, because we have now because here the data is that the resistances of phase B as well as phase C are also same as that of phase A, and also the radiuses of phase A as well as phase B are also same as that of phase A. So, then therefore, our ZBB and ZCC also would be equal to the same value. So, ZBB, ZCC also would be equal to 0.3733 plus J 1.4594 omega per mile. Now, what is ZAB? ZAB, we have said that it is RD plus J omega k log dE by DAB, right? That is what is the value, right. So, ZAB is nothing but, now what is the RD is 0.050958. So, RD is 0.09528 plus J into 0.12134 log DE is 2790 divided by DAB. DAB is nothing but the distance between phase A and phase B, that is 10 feet, that is given. So, it is distance between 2790 by 10. So, it will come out to be 0.09528 plus 0.6833 omega per mile. Now, as distance of AB is equal to as DAB is equal to DBC, that is basically the as the distance between phase A and B is also equal to the distance between phase B and C. So, then therefore, ZAB ZBC also would be equal to ZAB, that would be is equal to 0.09528 plus J 0.6833 omega per mile. Now, what is DCA? Now, what is ZCA? Now, ZCA is RD plus J omega k log DE by DCA, right. So, RD is nothing but 0.09528 plus J into 0.12, no, is equal to 0.09528 plus J 0.12134 log DE is 2790 divided by DCA. DCA is the distance between phase A and phase C. So, that is from here, from this diagram, it is 20 feet. So, then therefore, it is divided by 20. So, that would be is equal to 0.09528 plus J. If we do this calculation, it will come out to be J 0.5992 omega per mile. So, what we have got, that we have got the values of ZAA, ZBB, ZCC. So, we have got the values of ZAA, ZBB, ZCC, ZAB, ZBC and ZCA. Now, these values we have all got in terms of ohm per mile. Now, because the length of this line is 40 miles, so then therefore, to find out the impedance matrix, so this would be basically, it would be given by that essentially. So, then therefore, ZAA would be nothing but this into 40, ZBB also would be equal to this into 40, ZCC also would be equal to this into 40, ZAB also would be equal to this value into 40, ZBC also would be equal to this into 40, and this value of ZC also would be equal to this into 40 for the entire line. So, if we do this calculation, if we multiply of these values with 40, that is basically the length of the line, and then if we put them into an impedance matrix, so then therefore, the impedance matrix Z will look like this. So, then this value would be basically 14.932 plus J 58.376, then it is 3.812 plus J 27.332, it is 3.812 plus J 23.968, and then of course, it would be also 3 because it is symmetric, that we have already seen. So, it is J 27.332, and we have also already said that in this case the values of ZA, ZBB, ZCC are same. So, then therefore, ZBB also 14.932 plus J 58.376, and ZCA, ZBC is given by 3.812 plus J 27.332, and this would be 3.812 plus J 23.968, because it is symmetric, and because it is symmetric, so 3.812 plus J 27.332, and the last one is 14.932 plus J 58.376. So, this is total ohm. Now, what happens? So, then therefore, this is the Z matrix. Now, you see what happens is, now please note one thing. What happens, that I do have one 3-phase transmission line, let us say. So, now I have one 3-phase transmission line, 3-phase transmission line, right, and I have here the source, 3-phase source, this is the 3-phase source, this is the 3-phase, say, balanced source, and let us say that from at the load end there is one load connected 3-phase balanced load. So, this is the 3 phase balanced load. So, this is the case. So, 3 phase balanced load, and say that these currents are IA, IB, IC. Now, you see, if this is the Z matrix, and if I say that this voltage at the source side is, let us say, VSA, VSB and VSC. So, then therefore, and if I say that at the load side this voltage is VLA, this is VLB and this is VLC, right. S basically stands for source. So, S is stands for source, L stands for load, right. So, then therefore, clearly I can write down that VLA, VLB, VLC would be given by source voltage, that is VSA, VSB, VSC minus this Z matrix into IA, IB, IC. So, that would be the source voltage, sorry. So, then therefore, that is basically nothing but the load voltage. Now, if we expand it, so then therefore, what I will get, so then therefore, if I expand it, so then what I will get, VLA, VLB, VLC, that is the VSA, VSB, VSC minus ZAA, ZAB, ZAC, ZBA means ZAB, ZBB, ZBC, and then ZAC, then ZBC, ZCC into IA, IB, IC. So, then therefore, I can write down that VLA is equal to VSA minus ZAA, IA minus ZAB, IB minus ZAC, IC, and VLB is equal to VSB minus ZAB into IA minus ZBB into IB minus ZBC into IC, and VLC is equal to VSC minus ZAC into IA minus ZBC into IB minus ZCC into IC. Now, you can clearly see that even if IA, IB and IC are purely balanced, and even if VSA, VSB and VSC are clearly balanced, but because these elements ZA, ZAB and ZAC, they do differ from each other. So, then therefore, VLA, VLB and VLC, they will not be balanced. So, in general, even if I have a balanced source and even if I have a balanced load, but because of the effect of this transmission line impedance, right, because of this effect of this transmission line impedance, right, then even then the load voltage will not be balanced, it will be still unbalanced. And the more this Z matrix would be, say, and basically the more would be the difference among the values of this Z matrix, the more unbalanced would be the load voltage is. So, then therefore, to reduce this unbalanced, what it is done is we usually do something called transposition of the transmission lines. So, what we do, of course, this term is, I am sure this is known. So, then what we do is transposition of transmission lines. Right. So, what do we do in the case of a transposition? Let us say we say that this is position 1, position 2, position 3. So, we write that this is, so let us say that this is position 1, this is position 2, this is position 3, and then for some length this is phase A, phase B, for some length this is phase A, phase B, phase C, and then after some distance, phase A takes the position of 2, right, phase B takes the position of 3, and phase C takes the position of A, right. So, this is the first length, then this is the second length, and then again after some distance. So, after some distance what will happen is that phase A will come into this position, phase C would come into this position, and phase B would go into this position. So, then therefore, this is A, this is B, this is C, and then what will happen is that this is now B, this is C, and this is A. So, you see what happens is that in the, if this, I mean, total length is, let us say L. So, for let us say L by 3 distance, phase A will take position 1, phase B will take position 2, phase C will take position C. Then for the next length of L by 3, phase A will take the position 2, phase B will take the position 3, and phase C will take the position 1, and then for the third L by 3 distance, phase A will take position 3, phase B will take position 1, and phase C will take position 2. So, then therefore, in the entire length 1, 2, 3, so then therefore, in this entire length all the conductors, or rather all the phases will have the equal distance involving every position. So, then therefore, because of this the difference between the mutual impedances would be much less. So, this is called the basically the transposition of transmission line, and now we will try to see that how can we calculate the impedance matrix of a line which undergoes a transposition operation, right. So, to do that what we will do is we will introduce some matrix. So, that matrix is called, so we call it, it is actually called rotation matrix, but it is actually called rotation matrix, but it is actually uh, represents the transmission of the line. So, this rotation matrix R phi, this is called R phi, it is defined as 0, 0, 1, 1, 0, 0 and 0, 1, 0. So, and the this is, so this is, and this denotes the position. So, this is 2, 3, 1. So, now what is the effect of this transposition? Now, suppose let I define a vector v1, 2, 3 as v1, v2, v3, right. Now, let us see what happens if I do this operation R phi into v1, 3. If I do this operation, what happens? So, it would be 0, 0, 1, 1, 0, 0, 0, 1, 0, v1, v2, v3, right. So, then what will happen? It will be v3, then it is v1, then it is v2. So, you see third row comes at the top and then v1 and v2, and then basically, and then what happens? First row comes to the second and the second row comes to the third. Let us see that what happens if I do this operation R phi into z a b c. What happens if I do this operation and also let z a b c is given by some impedance matrix z a, z a b, z a c, then let us say z b a, z b b, z b c, z c a, z c b, z c c. Right. So, what will happen then? Now, if I do R phi into z a b c, so then it would be 0, 0, 1, 1, 0, 0, 0, 1, 0 into z a, z a b, z a c, z b a, z b b, z b c, z c a, z c b, z c c. Now, here you might wonder that I have not specifically taken this matrix z a b c to be a symmetric matrix. Well, what we actually wanted to show the property of this rotation matrix, and basically for that it is not necessary for this impedance matrix to be a symmetric matrix. So, then therefore, this property, as we will just now see, this property holds good whether this matrix Z A B C is a symmetric matrix or an asymmetric matrix. So, then therefore, as a result we have taken this matrix Z A B C to be any general matrix. It may be a symmetric matrix, it also may be a unsymmetric matrix, right. But we are only interested to see that what is the property. So, now if I now do this, so then what I will get? So, it would be ZCA, ZCB, so let me write it at a space is little less, but then let me try. So, it would be basically ZCA, ZCB, ZCC, right, and then ZAA, then ZAB, ZAC, and then it is ZBA, ZBB, ZBC. Right. So, then here what again we do, that if I do multiply R5, that is if I do pre-multiply this rotation matrix with a 3 cross 3 impedance matrix, it may be symmetric, it may be unsymmetric, what happens? That the third row becomes the first row becomes the second row becomes the third row. So, then therefore, it is as if a rotation in this direction, right. So, it basically denotes a rotation as if that these rows are basically being rotated in an anti-clockwise direction, correct. Well, this matrix has got some other properties also. So, then therefore, we will discuss all the other properties in the next lecture. Thank you.